Okay, so we are back. Are you ready? Get everybody's attention. So we're in chapter 6 now, and this is going to be mostly new for you. So brace yourselves. Chapter 6, conceptually, maybe one of the more difficult chapters, not to psych you out or anything, but it's also one of the most interesting chapters. So I hope you like it. So what we're going to do is we'll talk about thermochemistry and energy just in general, and we'll kind of ease into it. We'll talk about the first law, what are state functions. That's kind of interesting. Okay, internal energy, which involves heat and work. So we'll talk about heat and work. We'll talk about calorimetry, which is how we measure the heat released or absorbed by reactions. We'll talk about thermochemical equations, which involves Hess's law. Heats of formation, standard enthalpy. Thermochemical equations you had a little bit of exposure to in Chem 107. So some of it will look familiar, but it's sort of put in a different place. I don't know. So today we'll probably just get through maybe heat and work, maybe get to calorimetry, and then later we'll get to the rest. Okay. So let's talk about what is thermochemistry and applications of it. Here's a question for you. How do we know if certain reactions will occur, ... pause, without actually doing the experiment? We can look at thermodynamic data to get an idea if a reaction will occur or not. Especially next semester, you'll get to something called Gibbs free energy, and that's when you can really tell if a reaction is spontaneous or not. How are calories in food counted? So like if you look at a food label, like my nickname is Soup Can Fernandez, because I carry my pens in a soup can. So if I look at the label here, it says 150 calories. Okay, how do they know that? How do they figure that out? And so this chapter sort of addresses some of that. Can we get more energy through more efficient processes that are less polluting, right? So aside from the national debt, the energy crisis is probably my second biggest fear that we have. And I'm only worried more about the national debt because it affects how we address the energy issue. So can we get more efficient energy, without polluting? So apparently in California, I heard this the other day, I forget what the year is, but by 2035 or something, we're supposed to be getting at least half of our energy in California, more than half, due to renewable sources. We're actually ahead of the curve a little bit on that. So we get a lot of our energy already from solar and wind. If you drive out to Palm Springs, anyone been out to Palm Springs? I'm sure you've been out to Palm Springs at least, right? You've left LA, Orange County. Has anybody not ever left LA or Orange County? I hope you've left. I hope you've left and explored at least the neighboring counties. But if you drive out to Palm Springs, what you notice, you see these big wind turbines out there. And that drives energy production through renewables, essentially wind. And it's a perfect place to do it out there because when you're driving right in between the San Jacinto mountain range and the San Gorgonio mountain range. Between that, you've got this canyon that they're essentially driving through, and the winds blow really quite fast through that canyon. Okay, so something else that interests me. Can we build a self-sustaining city on Mars? So how is energy going to affect future generations when we actually are, and it will happen eventually, maybe not in our lifetimes, but we will eventually start colonizing planets. Unless we destroy ourselves first or asteroid hits us. Then we go to the wayside like the dinosaurs, but certainly some issues to be concerned with is, can we produce more efficient, more energy-producing rocket fuel? Can we have rocket fuel that has less density to it, so it weighs less, but produces more energy when you burn it? So it used to be that a trip to Mars was estimated to be about 2 years. Now it's down to about 9 months. So it's getting better. Okay, we're on our way. you want more details, call Elon Musk. Right. If you don't know who he is, just ask me after class. Okay. So what is thermochemistry? Thermochemistry, in a nutshell, is it's a quantitative study of energy transfer. And we usually transfer energy through chemical reactions. Sometimes you have a sample that's maybe heated up and it needs to cool off and that heat needs to go somewhere else. But what created that heat in the first place is always going to be some form of chemical reaction. Okay, so energy can be transferred from one system to another. The word system oftentimes is interchanged with reaction. So if you study a system, it's like you're saying we're studying a reaction, right? That's sort of the lingo that goes along with thermochemistry. Energy can be transformed from one type of energy to another. So we can produce chemical energy in the form of bonds, and we can carry out a reaction, and then that is converted to thermal energy. That thermal energy can then be used to do work, or which is another form of energy. All right. Thermodynamics is a macroscopic view of chemistry. All right. What do I mean by macroscopic versus microscopic? You can see with the naked eye. So we observe macroscopic changes in matter through bulk changes in matter. Right. So we're looking at things we can see. Okay, so bulk changes in matter can be seen with the naked eye. That's really what we're looking at with thermochemistry. What is energy? Okay, it's something we all wish we had more of, right? Wouldn't it be great if you didn't have to sleep? Right, you know, and wouldn't it be great if you didn't have to eat? Well, maybe for some people are like, I kind of like eating. I kind of like eating food. I'm not a foodie. I hate eating. I don't like eating because it takes time. The most precious thing that we all have is time. Not money. Money's sort of like time, but not exactly. It's a different allocation. But if I didn't have to eat, I'd be so much happier. If I didn't have to sleep, I'd be so much happier. It'd be great if I could just, not have to do those things. But I have to because I need to save my energy to do work. So if I didn't sleep, I didn't eat, I couldn't do work. And if you can't do work, then you're basically not alive. So there's two main forms of energy, kinetic versus potential energy. Kinetic energy is what? Do you remember? The energy of motion. If something is moving, it's got kinetic energy. It kind of goes back to when I was talking about gases. What has the highest kinetic energy? Hulk or Flash, right? They're moving at different speeds, but they've also got different masses. So kinetic energy is, but they're moving, okay, they're running at you. So it's the energy of motion. Potential energy is stored energy, right? So a lot of the time what happens is that you will convert potential energy into kinetic energy to do work, okay? So speaking of potential energy, potential energy is stored energy, but what do we mean by that? Well, water stored in a dam is an example of stored energy. The water hasn't flown over the dam yet. It's sitting there resting behind the dam. It's just waiting to just fall through the dam, right? And one way that we can generate electricity through non-polluting sources is to say, well, if we have a dam, we can have a hydroelectric turbine built into the dam, and the water flowing over the dam turns the turbine, which creates electricity, right? So, but until we let the water flow over the dam, we don't have electricity, right? So the water being stored in the dam is an example of potential energy. It has the potential to want to fall over the dam. We all have potential, right? Right. And so we all have the potential to fall over the dam. In this case, the water's falling over the dam. If you stretch a rubber band, okay, it's also an example of potential energy. It's just it wants to snap back, right? When electrons and protons are getting close to each other, they want to come together and form a bond, right? That's potential energy. So this idea of potential energy, things wanting to happen, whether it's electrostatic forces versus gravitational force, or these things, it's all forms of stored energy. Chemical bonds are a form of stored energy. Okay, also a form of stored energy would be food and gasoline or coal. All of that stuff is just waiting to be oxidized. All right, so here we go with chapter 4 material. I'm kind of tying in different ideas from different chapters. So food, gasoline, coal, all of that when it's converted into kinetic energy is being oxidized. Okay, so think about these big picture things as we go. So kinetic energy, once we've oxidized and once we've gone through all these chemical reactions to generate energy, we can convert that into kinetic energy. Now, just to get a little corny, but I still think it's a little entertaining, I'm a comic book guru, so sometimes I bring up this character from the comic books. His name is Sebastian Shaw. He's a villain from the X-Men, and also if you've ever seen the movie X-Men First Class, he was played by Kevin Bacon, the actor, and he has the ability to absorb all kinetic energy and store it, and then he can reuse that to destroy people. You know, that's kind of his ability. So water flowing over the dam is kinetic energy. Him destroying his opponents is kinetic energy being given back out. If you've never seen the movie, it's pretty good. I liked it. I thought it was one of the best comic book movies. Gasoline actually burning is an example of the kinetic energy. It drives the drive shaft of our wheels, right? Going for a run, there's a novel idea to get some exercise. I should take my own advice and do it, but I haven't done it this semester. So when you go for a run, you're converting that stored energy that you took in the form of food, and now you're running, right? And having kinetic energy. So what are the two main kinds of energy? We have kinetic and potential. We convert potential into kinetic energy through chemical reactions. A lot of those chemical reactions are oxidation reduction reactions. Okay, that's pretty much the big picture of what I'm saying so far. Okay, here's some energy units. The SI unit of energy is the joule. Some useful conversion factors, and some of these you've seen already. 1 joule is equal to a kilogram meter squared per second squared. This is a useful conversion when you're dealing with kinetic energy. Look up velocity, you've got meters per second. This is more of a physics conversion, but still useful. 1 joule is equal to a Newton times a meter. Here's another conversion that we'll use in this chapter. 101.3 joules is equal to a liter times an atmosphere. That's used in pressure volume work. Here's for your foodies in the room here. 1 calorie is equal to 4.184 joules. 4,184 joules is equal to a kilocalorie. So you can use calorie as a base unit in the metric system. And here's a prefix, kilo, right? Kilocalories is a metric unit. And then 1 joule is equal to a watt times a second, so that's useful for electricity. One thing about food, it says here, if I turn on the dot cam here real quick, let's see if I can focus it. My soup can's been through better days. So let's see if we can focus it on here. All right, and we'll zoom in. There we go. So you see the food label? Look at the word calories. Okay, it's right there. Okay, and now let me switch back to the slide real quick. And look at the calorie written there. Do you notice anything different? There's a capital C on the food label, and there's lowercase c here. So, getting back to the label, okay, instead of writing capital C, what unit could they write there? They could say kilocalories. So the capital C means 1,000 calories. So if it says 150 big calories, that'd be the same as saying 150,000 little calories, non-capitalized. So if you want to mess with somebody, who doesn't know that, and they're talking about, trying to curb their calorie intake, you say, don't eat that, it's got 150,000 calories in it. And they're like, what? And they kind of go a little, they're like, just kidding, it's only 150 big calories, but it's 150,000 little calories. And a lot of people don't realize that there's 2 different kinds of calories.